So hello everyone, my name is Aniket Rangrej and I am data scientist at FogHorn Systems, India. So I am here to talk about advanced image recognition with mask RCNN. So machine learning can be applied to various use cases in computer vision, right? Starting from classification to instance segmentation. So if you consider the first image, the task is to identify whether an image contains an object or not. This is just plain classification. So this classification can be a normal binary classification, can be multinomial classification. So this is a fairly simple problem to solve based on the current state of art work in machine learning and computer vision. In second figure, if you see, the task in second image is to classify the image as well as the localization of the object. So you can see the cat, but where exactly the cat is located in the entire image. So that is nothing but the localization. That is to find out the exact bounding boxes around the object. If you look at third image, the task here to identify multiple objects and localize multiple objects. So there can be some overlapping among the objects, and so there can be multiple objects. Then it might be the case that there might not be any object at all in the image. So this is more like a generalization of classification plus localization, which is nothing but the object detection. In last image, if you can see, the task is to identify pixel by pixel and the object in the image. So finding exact mask around the object is kind of tougher task than all other tasks. So to solve the above challenges, I am going to walk you through different techniques around RCNN and its variations to solve the mask RCNN, to solve the instance segmentation and object detection. So first we will look at RCNN, then we will discuss drawbacks of RCNN and how faster RCNN has solved those drawbacks, and then drawbacks of fast RCNN, so and so forth. So let's start with RCNN. So RCNN is nothing but the region proposal plus convolutional neural networks. So if you look at first image, we need to identify the different objects in the image. So there is a horse, there is a human present over there. So if you look at the second image over here, so there are some region proposals present, and those region proposals will be an input to convolutional neural networks. And so we will be having a SVM classifier, which will be per class classifier. So that is this an aeroplane? Does the region contains aeroplane or not? Does the image contains person or not? So it is basically a binary classifier, which is at the end of convolutional neural networks. The input to the classifier will be convolutional feature map. So to start with, so once we have data sets, there will be external region proposals, and which will give region proposal, and so those region proposals will be stored on the disk, and then once it gets read from the disk, it is going to pass as input to CNN, and so the output of CNN will be feature map, and then it goes to classifier. So this is the general architecture of RCNN. So approximately, according to the paper, there are 1,000 to 2,000 region proposals per image they provide generally based on selective search strategy. So let's look at how external region proposal works. So as we saw in the previous diagram, so RCNN requires external region proposals, which is the first step in RCNN. So let's consider this particular image. So what selective search does, it starts with, so this is one of the way to handle the region proposal. There might be another ways, but I'm going to talk about the segmentation approach. So let's start with over segmentation. So that is try to segment the image as granular as possible, and then apply some greedy method like hierarchical clustering to merge the granular segments into higher level segments and so on and so forth until the single region, that is the whole image, is a region proposal. So, for example, let's say initial granular level is, let's say, 1000 granular segmentation we have formed, and then from 1000, so one by one in hierarchical clustering, so based on some distance measure, we club different segments and we create a single region. So the distance measure for this, they use the size as well as the texture. So lesser the size, they give more preference because it's more likely to segment two minor segments as object rather than the bigger objects. So that is the reason they give priority to size. And the texture, they use shift features and they use histogram interaction between these features, and they perform the distance calculation. And based on that, the single unified region is formed. So all these region proposals, starting from granular level till single level, single region, so all these features can be input to CNN. So we can do some optimization over here as well. So for example, all the dense regions can be input, but this, for example, this particular object or region is not very densely populated based on the initial segmentation. So this can be skipped for the input to the CNN. So this is the optimization we can do. Then let's look at the drawbacks of RCNN. So first of all, it is a multi-stage pipeline. So first stage is external region proposal, which is a little bit time consuming because it is based on selective search. Then it is classification. So classification in the sense whether particular object is present or not in this proposed region. So if it is present, then third stage comes into picture, which is finding out the bounding boxes, which is the regression. So they don't use a multi-task loss, but they use single task loss in different stages of their pipeline. So that is the reason it is expensive. So it is expensive in terms of space as well, because the region proposals which they find, they store onto the hard disk, and which consumes hundreds of gigabytes of space. So also it is expensive in terms of time, because there is no feature sharing among the regions, because so each region proposal is input to CNN, not the original image is input to CNN. So that is the difference. So even if multiple regions from the same image are input to CNN, so there is no information sharing, because there is no projection of region proposals to the original image. So the object detection is obviously slow. So fast RCNN, what they have done, they tried to tackle this problem, and they tried to come up with ROI pooling layer and multitask loss, which is the unique in RCNN kind of hierarchy. So what they do, instead of sending region proposals to convolutional neural network, they pass entire image to convolutional neural network, and then external region proposals, they project it on the convolutional feature maps. So we have already convolutional feature map based on the original image, and then they pass region proposals and they project it on the convolutional feature map. So there is information sharing. So for example, if there are 100 region proposals in an image, and so one image processing can be at maximum faster 100 times than the original RCNN. So that is the way they try to achieve the time performance. So once you project region proposal onto convolutional feature map, So they have been using fully connected layers. So the input for fully connected layers should be fixed size. So that is the reason they have come up with the ROI pooling layer in between convolutional feature map and fully connected layers. So the main purpose of ROI pooling layer is to, so for example, in this image, I can explain you how ROI pooling layer based on this diagram. So consider this is the original image, which is 8 by 8 pixels, which is fairly small image, but for example purpose, we can see. And region, this is the black bounding box is the region proposal, which is 5 by 7 pixels out of the 8 by 8 image. So, and input to the fully connected, let's assume it is 2 by 2. So we need to divide this region proposal into 2 by 2 based on some aggregation. So what they done, since height is 5 pixel and width is 7 pixel, we had to truncate some of the floating points. So first region, first section will be of 2 by 3, then 3 by 4, then 3 by 3 and 3 by 4. Yeah. So based on this, what they do, section wise max pooling they perform over here, and maximum is 0.85. So they put 0.85 over here, 0.84 is here, 0.84 is here. So based on the max pooling, they come up with some features which is of fixed length, which is input to fully connected layer. And once they apply fully connected layers, they have multitask loss over here, which is the softmax plus regression loss. Softmax is basically for classification, whether which object is present and corresponding the bounding box. So which is given by bounding box security. So the loss function is unique. So there is no need to have separate stages in same pipeline, but unified loss function can be applied. So in fast RCNN, there was, since they have used a single stage pipeline, but there was still a drawback, which is depending on the external region proposals. So in faster RCNN, they just introduced a region proposal network layer, which itself proposes regions. So we are not depending on the external region proposals over here. So whatever feature maps we get, that feature map will be input to region proposal network as well as ROI pooling layer. So region proposal network will give the actual bounding boxes and which class is present in particular region, and that will be input to ROI pooling layer. So for ROI pooling, the region proposal and feature maps will be input, and the remaining process is as it is based on the fast RCNN. So now let's look at how region proposal network works. So for example, this is a convolutional feature map over here, which is nothing but the output from convolutional layers. And we can set the number of anchor boxes we need to use, the shape of that, and we can even use different scaling factors, different aspect ratios for these anchor boxes. So let's say in this example, there are k anchor boxes. Okay. So for example, we can take 3 anchor boxes, first one, second one, and third one, and we can scale it by 3 times. For example, so 3 will become 9. So each of the anchor boxes will scale 3 times. So there are total 9 anchor boxes, and what we will do, we will just slide the window over the convolutional feature map, and for each feature map, what we'll be doing, we'll be maximum able to find the number of regions which is equal to 9, because 9 number of anchor boxes are present in our case. So this will be applicable for each of the window. So at max, if we use stride as 1, then the dimension of the convolutional feature map minus 2 into dimension of convolutional feature map minus 2 into 9. Those many maximum region proposals can be proposed, and which can be input to ROI pooling layer. So here there is also convolutional layers which outputs you the class and regression bounding boxes. So which exactly denotes the actual region properties, and which will be input to RF layer. Do you have any questions? I can see.
Any questions from the audience? No, Aniket, proceed.
Okay. So there is a small problem with ROI pooling layer, which needs to be handled when we try to solve the instance segmentation. Because till now, what we are seeing is we are trying to mark bounding boxes around us, but not exactly pixel by pixel level.
Aniket,
So
hold on for a second. There's a question.
Just click on the chat.
Okay. There's a question in chat.
So is there a good rule of thumb for selecting the size of the overlap for sliding window, given computational constraints? Or does the algorithm take care of this? And is the pixel size of the bounding box a hyperparameter?
I don't think you can hear that. Okay. Can you see the question in the chat?
Oh, okay.
It's too small to read.
Are the external region proposals completed manually? So no, external region proposals are based on, it can be based on selective search, sliding window, it can be based on segmentation, but it is not based on manual labels.
Okay. Robbie, does the more box work? More?
So these are the probable objects based on the segmentation, not based on manual labels.
No, it's too small. Like it's very difficult to see.
Click on the word 49, the red text 49.
I
Okay.
think
Yes.
there are multiple questions, I think.
Yeah. I can't see from here. Do you want to repeat? I'll just repeat the question for you. Is there a good rule of thumb for selecting the size of the overlap for the sliding window? Or does the algorithm take care of this for, and is the pixel size of the bounding box a hyperparameter?
Okay, so if you keep sliding window size very small, so that there is definitely a threshold that has to be applied based on the use case. So if you want to have many region proposals, then you can keep sliding window size very small, so that then super sliding window there will be k into some scaling factor number of region proposals. So that is depending on the size of the object you are trying. So again, that is it's not straightforward answer.
Okay. Why don't you proceed with the presentation, Aniket?
No.
Okay, go ahead.
Okay. So problem with the ROI pooling layer is it basically quantizes the information. For example, so starting from the initial image till the end of output,
Should I close it?
Yeah,
we
just
are
go and close it
quantizing
because you can open it again by
two
clicking
times
on the chat
in-
in the bottom center.
So first quantization is happening at CNN level, and second quantization is happening at ROI pooling. So let's look at first quantization now. So let's say image is of 800 by 800 size, and we have an object which is 665 by 665, and this is input to CNN which is 16, for example, and output will be fraction of 32 of the original image, because VGG 16 it shrinks the output because of feature extraction. So output of CNN will be 25 by 25 pixels, and if you project this particular object to a picture map, then it will be of 20 by 20. But what we can see here, we were able to directly fraction 800 by 32, which is 25, so there is no image loss. But if you look at here, 665 divided by 32 is nothing but 20.78. So 0.78, so we need to either make it 20 or 21. So there is some loss. So let's look at why this loss is important. Because 0.78, it looks like it is very small number, but if you look at here, so this 1 pixel in feature map, it represents 32 pixels in horizontal image. So 0.78 into 32. So that is a bigger loss if you are trying to solve the problem of instance segmentation. So this needs to be solved. And second time, quantization is happening when we are passing this to ROI pooling layer. Again, we are since we want fixed input size at the fully connected layer. So for example, in this case 7 by 7, so we need to divide this 20 by 7, which is 2.86. Again, there is error of 86.86, and so again there is a quantization loss. So to solve this ROI pooling layer problem, in mask RCNN, what they proposed is using bilinear interpolation instead of just ROI pooling. So we can apply simple linear interpolation as well as bilinear. But since we are tackling with two-dimensional image, so we used bilinear interpolation. Basically, difference between linear interpolation is and bilinear is we are interpolating values between based on one axis in linear interpolation, and in bilinear interpolation we are using both the axes. And right. So let's look at how it works. So in this image, for example, 5 is the height and 7 is the width for the region proposal, and we need to convert it into 2 by 2. So earlier we saw we apply ceiling and floor to the fraction we got by dividing 2. So now what we are going to do is we are not going to seal or floor the values, but we are going to keep the values as it is. And what we are going to, so we are dividing this complete region into 4 equal sections, and each section will put some sample points in equal distance of based on distance. And let's take example of this particular sample point. Then this sample point is going to gather information from this point, this point, this point, and this point. So it is going to get information, but how much information it should gather from this point and this point is based on its distance from. So let's assume this is y1 and this is x1 in terms of this is y1 and this is y2 in terms of x-axis. So y2 is more near for this sampling point than the y1. So it will give more weightage to this particular axis than this. So that is given by 1 minus this particular distance region. And x minus m is nothing but sorry, it was x1 and x2, not y1 and y2. So x minus m is because we need to take distance from x1 as well as x2. So if you subtract this, m minus x, then we will get a positive number. If you subtract m minus x2, then we will get negative number. So that is the reason we are using the absolute value. And so once we get the some weight based on the x-axis and some weight based on y-axis, then we multiply and as a consolidated weight and multiply with the value. So this is the output of the ROI align based on the bilinear interpolated values, and then we can apply max pooling out of this. So max pooling values will be input to the fully connected layers. So the advantage what we are getting over here is instead of getting pixelized input, so pixelized input is not very good to solve the problem of instance segmentation. So we need to smooth that just to get the good boundary around the object. So that is the reason we are smoothing it. based on the bilinear interpolated values. So let's look at the loss function and how it is different from loss functions for the previous RCNNs. So in original RCNN, so it was basically three-step process. The first step was the region proposal, then second step, which is first step in the actual network, is classification. If our object is present, then it will go to second step, which is bonding box segregation. So this is kind of a little bit slow, but it works. But in fast and faster RCNN, they come up with the multitask loss, which is nothing but a combined loss in classification as well as bonding box segregation. So it is nothing but loss equal to loss of class plus loss of bonding box based on the some weighting factor. And in mask RCNN, they have introduced mask loss, which is basically mean binary cross entropy loss, which is nothing but summation over y log y. So that is binary loss. So you can get the idea of how loss function works and next slide. So for class loss, they're using normal log loss, and for regression loss, they're using smooth L1 loss, regular loss. So now we looked at different loss functions. We looked at ROI pooling layer, ROI align layer, and internally it uses ROI max pooling as well. So let's look at complete architecture behind the mask RCNN. So let's say the image is an input to the convolutional neural network, which outputs the feature maps, and feature maps is input to ROI layer as well as input and proposals. Region proposal itself, based on some sliding window and some number of anchor box threshold, it will propose some of the regions, and based on those regions and input from the feature map, ROI pooling layer, ROI align layer will come into picture, which will give fixed size input to fully connected layers, and also it will give input to mask layer. So which is nothing but a convolutional layer. So based on this, loss computation happens. This forward propagation and back propagation is similar as a faster RCNN. This is nothing but the extension of faster RCNN just by introducing binary loss based on mask. Okay. So let's look at the speed and accuracy performance comparison in this slide. So I have not talked about SST and YOLO, which are pretty good algorithms if you want good speed. But since mask RCNN is assumed as a descendant of faster RCNN, so faster RCNN it performs much better in terms of accuracy than fast RCNN, and speed-wise it is little bit fast than fast RCNN. So mask RCNN will lie somewhere around here. I have not mentioned it, but somewhere lie around here because it tries to get use of mask loss. So that's why there is hamper of little bit speed, but accuracy-wise we'll get exact masks to detect the object. That is the advantage. So evaluation measures. So similar to other applications in machine learning, here also we can use precision recall. So in this case, precision will be nothing but intersection of ground truth object and the predicted object divided by the predicted object. So it is pixel by pixel values comparison. So that this pixel lies here or not. This can be based on bonding box. This can be based on actual masks. So depending on the problems. So also recall is important because out of this many objects, how many objects we are trying to identify correctly and with what accuracy. So that is also important. IOU is good measure in case of object detection because it tries to get the complete, get the advantage of both. So it's intersection divided by union of the both ground truth object and detected box. So in general, in detection, we say 0.3 or 0.4 as a poor IOUs and 0.6, 0.7 are fair enough IOUs, and 0.8 onwards, we can assume it's giving a good idea. So in our experiments, we kept 0.6 as a threshold for the intersection of over-union. Also, mean average precision is important. For example, we calculated precision, we calculated recall. But let's look at this particular example, second example. So for each recall, what is the maximum precision? If we calculate that, and if we mean of all those values of maximum precisions, then we will get mean average precision. For example, for 0.0, we have got precision 0.2, so we are not considering that. For 0.17 recall, we have got maximum 0.5 as a precision. So that's why we have kept 0.5 here. Then 0.33 recall, we are getting 0.4. That's why 4, and so on and so forth. 0.67, maximum is 0.57, so 2.2. So mean of that will be 0.32. So we are getting approximately 0.8 as MEP in our experiments. So these are the experiments we tried out. We tried out on different architectures as well, but I'm going to show one of the experiment result. So which is nothing but we used ResNet 50, which was trained on Coco dataset, and we did transfer learning by placing some layers. And training images, we were having small training examples that we fetched, and we were trying the transfer learning on that. And validation images were 50. We tried it for 100,000 iterations, 100 iterations with batch size 1. Training took around 10 hours. IO threshold, as I mentioned, it's 0.6, and different data augmentation strategy we used. We can increase based on the whatever we need. So we tried horizontal flip, brightness and contrast adjustment, and color dispersion. So prediction time was approximately 0.4 seconds on GeForce GTX 100 Ti with 12 GB RAM. So this was our experimental GPU configuration, and we got mean average precision as 0.2. Okay, so these were some of the results of the test data. We tried on flare and smoke predictions. We captured some public images from Google, and we tried to find exact smoke and exact fire locations pixel by pixel using mask RCNN. And so if you look at image 1 and image 2, so it's taken from the same location, but the smoke here it has increased, and mask RCNN has captured it really well. If you look at third image, there is overlap between bonding boxes, but still mask RCNN was able to figure out the distinguish between smoke and fire depending on the entropy loss. And this is not sensitive to just day. This is at night also we got fairly good results. Those results we are showing over here in the last image. So these were some observations we got based on the mask RCNN. There are multiple uses we can use out of mask RCNN to find the exact detection. So depending on the use case. So that is the end of my presentations. Now we can have different questions.
What is the version of YOLO in the slide comparing algorithms? Do you have that? I don't think he has it.
No, so we don't have exact versions of the comparison, because it's kind of general comparison based on different versions. So
Yeah.
This is the reference we took it from.
Yeah.
But in general, performance will be like similar to this. So
Yeah.
GPU version is different. Relativeness will be a little bit different, but in general it will be same.
Yeah. Let me answer the question. I believe it is version 2. I believe it is version 2. It's not version 3.
So because I was on version 3 and
Yeah. Any other questions? So Aniket, the question is the training data set did we create on our own? with the labeling. Let me answer that question.
Answer the questions you know.
Yeah. So we are going to show you a demo how we did it. So you'll get the answer. The answer is yes. We labeled them ourselves, and I'll show you how we did it. The question is, where does RCNN fall in this object detection performance comparison? It should be the speed should be very low. It should be very low.
Take axis here, so it should be somewhere around here.
Yeah.
In general, RCNN is 9 times slower according to performance comparison than fast RCNN. So it is much slower than fast RCNN. So will not fit exactly in this figure, but somewhere around here.
So it's for academic purposes. We just look at it. That's all it is. It's really slow. Basically, looking at segments one by one over the whole image and start doing the classification. I have not seen it myself. I think it's pretty low too. There too. Okay.
What was the algorithmic question?
The question is RCNN, right? So if you have an infinite computer power where you can have zillions and zillions of regions, then of course you can bring it to pretty close to 98%, right? In practice, it's not possible. Any other questions? Okay, then we'll go on to the next one, next presentation. Thanks for being with us this evening. I want to do a small demo. I can't do the complete training demo following what Aniket was explaining. I want to share what we have experienced so far with masked RCNN. Okay, so this is the experiment we did. Basically, what you see here is our use case here is to detect fire and smoke, similar to the one what Aniket was talking about. So you look at a chimney. We want to see whether we can capture whether the fire is there or not, what is the approximate area of the fire, and whether there's a smoke there or not, and also what is the approximate area of the smoke. That is very important for some use cases. When the smoke to fire ratio is beyond some threshold, we have to alert people. That's the use case. Go ahead.
Just a comment. So imagine if your car was burning lots of black smoke. That would be a symptom of a problem. Here we're working with natural gas production, and we're looking at what are symptoms of a processing problem upstream.
Okay. So in our case, the total solution will look something like this. So the video signals are sent to a masked RCNN detector, right? It's a model running up there. It will detect the fire and smoke, and as I said, it will also calculate the area and the coordinates and all those kind of wonderful things, and that will pass on to our application, which will do the downstream processing. So we're not going to worry about that. It's a complex event processing, which will basically provide the business value. So let's first focus on what this masked RCNN is all about, how we did our experiment. So here comes the TensorFlow object detection APIs. So Aniket went through in detail on how masked RCNN works. It's pretty complex. You've got 3 loss functions. It does all kinds of messing around with the algorithm. Finally, you have to train it using lots and lots of images. But TensorFlow object APIs has done the job, made the job easy for you. So it's an open source framework built on top of TensorFlow. That's one thing. With this you can easily construct a masked RCNN, and they also given you pre-trained models for you. So you can just use their models and train on top of it without having to worry about all this complexity. The masked RCNN support came into picture from February 2018, so it's fairly new. It's very new, okay, and they're making lots of progress as we speak. The pre-trained masked RCNN models available are 3 of them are available right now: ResNet 50, ResNet 101, and Inception V2. And there's a link there. You can just go to the link and read all about it. They're going to give wonderful example programs which you can use, configuration, everything is all there. So you can just use it. Okay? All right. So for every model which you choose to use for training your own masked RCNN model, there are multiple configuration available. Like you have to select what type of model you want to do, what is IOU threshold, you can put that, and loss weights. There are 3 loss weights, right? Aniket explained that. One is the localization, which is where the bounding box is, and the classification, what kind of object it is, and mask prediction, drawing the boundary around the object. So all these have different losses. You can actually give different weights to them based on your use case, and basically as part of the tuning method. Then maximum detection, how many objects you want to detect, what is the optimizer you need to do, right, in terms of momentum and other things, you can actually specify. After certain steps, change the and the weights, no, not the weights, and actually the what is it called? What I mean? As part of back propagation, you basically increment the weight a little by little, right? That you can change those numbers pretty easily. So also pre-trained model weights are available for you to use. Since pre-trained model weights are available to use, we could actually create a model using 200 plus images. Otherwise, you need lots and lots of images to create a model like this. It's a beast, right? All right. This is some of the training samples. One gentleman asked about the mask creation, right? We had to do all these things ourselves. If you see here, this is the image, right? This is the image. Below that is the mask. In this case, fire is the class and this is the mask. Are you following this? And here we have got two fire. You can see that. And for this fire, there is a mask here. And for this here, there is a mask. All right. The third one.
Oh, just a comment earlier in the text, a remote person had asked about the previous slide deck where there's a rectangle. Why are there rectangles? Where's the masking? But just to be explicit, there was like a green shading. That was the irregular mask over this object, or a blue shading. So a lot of times with these, they show shading to show the mask that's kind of an off color. The bounding box is just to make it more obvious. But when we're labeling the data, it's with the irregular shape. When we're scoring the data, it's with the irregular shape.
Yep. Good point. Had this been a regular object detection, your mask will be just a rectangle. You will have a rectangle. Here actually we are giving the actual shape of the object itself. Here you can see this particular image has got a fire and as well as smoke. The smoke is shown here and the fire is shown here. This is how you have to start labeling the data. So how do you label the data? There comes another open source tool, right? We got the link here, and this you can go, we'll be providing these links to you. Just go there and I'll just quickly show you that one. So this is a tool. This is an online tool. You can actually get the tool from, you can get something else also. Let me add a file here. Let me see documents. Give me 1 second.
I'm trying to let them use two hands.
Where is my, okay, all right. I just take a random image. So I got a random image here. So this doesn't have any masking done. The label is not created. All I have to do is this is my irregular mask, and I just keep clicking on nicely on this one. Done. So the mask is created. Okay. So and I can again click. That is, this is. I'm not a good drawer here. Sorry about that, but you get the idea.
So
right?
if even he can do it, certainly you can.
Okay, double click, it's done. So now what it's done is I created one mask here, another mask. It is put 1 and 2. 1 and 2, this through 2 classes. So it will create the annotation file for you. Later on, you can use it for training purposes. So let me go on to my PowerPoint here and go back.
Did you label the noun that you passed?
No, it's 1 and 2. Later on, you have to see what 1 and 2 is.
Okay.
So this is what we did. And as Aniket was mentioning, so we took 250 images and went through the labeling process. It's not trivial, but you have to do it. All right. So this is our training environment. Single GPU, training data set 250, validation data set 50, and models used all the 3 models. Resident 50, Resident 101, and Inception V2. We used all those 3 models. Okay.
So Greg, I got a question. That was the for flame. It seems to me I'm sorry. Question. It seems to me for flame, you can just overexpose a portion of the image and create a mask out of that pretty easily.
Yeah.
Especially for oil multipliers.
Yeah.
Because in
So what's the question again? I didn't get the question.
you need to use this tool. You can go on and do this thing automatically with relatively simple image processing techniques. You don't need to use deep modeling, you don't use anything. You just need to go on and basically take a negative and see what's overexposed.
Okay.
So part of it is you could have 4 smokestacks. Some may have fire, some may not. And then there's the smoke. And so we can look at both the attributes of the smoke and fire and which ones are associated with each other. And also you could have overexposed areas that are not fire, that are just a reflection off of some metal.
The caveat to that is this is actually in some desert where there is sandstone, and also the sun will be on top of the chimney. You could misclassify that as fire. So there's a lot of other challenges. So these kind of models will be better than the computer vision thing.
Yeah. So there are other options like, but those would be very intrusive. You can go and put a sensor there on the chimney everywhere, right? It's expensive and it's more intrusive. This today.
My point is in terms of creating samples for this thing, you could go on and simply create the samples very quickly doing that and potentially eliminate the stuff that's the sun just by striking it. You don't need to draw a polygon by hand around it. That was my
Okay, all right. Okay, so let's go. Again, I'm just reiterating the mean average precision and as well as IOU. I think Aniket went through this, so I can skip this piece. So these were the accuracy measurements we were using. So I won't go through this again. All right, so what you see here is a result from the Inception V2 model training for the mean accuracy precision of it shows the MAP at 0.5 IOU. That's what it's showing. And I trained this up to 20K steps. I think if I go beyond, I may get something better, but right now it's around 82% accuracy. That's pretty good, right? And it took around 3 hours to do this training. Okay, so all this could be done because TensorFlow APIs are available, pre-trained models are available. You just slap in 250 label data and you get some good results. That's the Inception V2. The next one is ResNet 50. That we did 1.5 hours to train 10K steps, and we were in a position to get up to 84%, 83%.
And this was GPU trading, NVIDIA 1080?
Yeah, this is a GPU machine, single GPU machine doing the stuff, right? All right. The next one is the ResNet 101. This was giving us up to 92% accuracy. This is the best so far. But it was pretty slow to train. For 5K steps, it took around 2.5 hours to step. So we had to do up to 20K. So it took quite some time to get this training done. Okay. So these were the results. And beyond, what do we do? So right, for tuning models, you can increase the number of weights, the number of steps you can do. You can change the loss weights, relative loss weights. You can do that. You can include dropout, and you can change the optimizer settings. And you can even use more augment images. You can do all these kind of things. This is in progress, by the way. That's what we are sharing with you. Of all these things, the number of steps, loss weight, dropout, optimized setting, this is all part of the configuration what TensorFlow has given you. So just change the configuration, rerun it. It's pretty easy to do. You don't have to write any single code in terms of changing the network and other things, which is pretty good. This is the comparison of the results. If you see here, ResNet from size-wise. Size is pretty important to us because we don't want the models to be fat because all our software, everything works on edge devices. We want it to be as lean and agile as possible. So ResNet 50 is 145 MB followed by ResNet 101 is 221 MB. It's pretty fat. And Inception V2 is 67 MB. It's the most lean. This is the number of nodes in the graph. The average accuracy I just talked about, the best accuracy is ResNet 101. And in terms of speed, if you see, this is kind of interesting. Inception has got the best speed, which goes in size with the size. Even though it's less accurate, it's got a very good speed. Followed by ResNet, 0.3 seconds for one image. And ResNet is 0.64, which is pretty bad. It's not that accurate, and it also takes more time to do it. So it's not good at all.
And these inferencing is on what compute platform?
This is the same GPU machine. Again, this is the way you should look at these numbers is relative. If you have a faster hardware and other things, things will change. But the expected relative numbers are expected to be the same. Question?
What is the size of the input images that you used?
Can you repeat the question?
The size of input images we used, 400 by 600?
400 by
600.
Yeah. Was there another question farther back?
Do you have accuracy numbers for smoke separate from fire?
Those are two classes. It's as if,
Yeah, he's just asking if we have them separately. We do internally for our internal project. For this presentation, we're doing more summary level.
yeah. So, but those are two different classes. And using the information we gather based on fire and smoke, we do a lot of things behind the scenes. Go ahead.
Some basic question. So when you're saying you use pre-trained networks, that's obvious, and you retrained only the final classification layer, right?
The fully connected layers, yeah.
Fully connected layers,
Yeah.
right? So when you say that, that means that you trained it on all the thousands of classes that were trained, and it was 1,000 plus 1, or it is trained on some other classes? How many classes of images do you?
Yeah. So the question is the original pre-trained model has been trained for 80 plus classes in this situation, right? And when you do a transfer learning, do you train for 80 plus 2 or just 2 classes? That's the question, right?
80 plus 2 or?
No,
Yeah.
That's the question.
That's the question. The answer is in any not only for this, any transfer learning, when you do transfer learning, we just use a feature extraction from those weights which are available, and we train only for the classes we want. That's it.
For the classes you want.
Yeah, that's the only thing we do.
And other.
Yeah. It need not be a subset of what they have done. Whatever the pre-training, whatever they did, it's based on all the feature selection. We just borrow the feature selection from them, and just we do only fire and smoke. They probably didn't even care about fire and smoke.
How many classes?
2.
2 classes. We don't use,
Yeah.
we don't use an other because we don't want it to recognize other. So we just train it on the 2 classes we care about. It's not like a 1 of n binary encoding output where you have A is true, B is true, something else is true, and it's only one of those 3 is always possible. You know, an image could have nothing, and then we want the output to be nothing.
Right.
Okay. Any one more question?
I'm just wondering why the ResNet 50 is half as slow as the ResNet 100.
I don't know.
Okay.
I don't know. By looking at the ResNet 50 means it's got less graph, which means less computation. I was surprised by looking at it. That's why I did this again and again to make sure that I was getting the right result. But that's what it was.
Is there something going on after that first image recognition layer that's different?
Well, it might be because of percent connectivity between layers. So if you have a ResNet 100, I'd have to check. I don't know. But it could be that if it's like 50% connected versus a ResNet 50 that's 100% connected, that could have a huge impact. And also the layer size between connections could have a huge impact. So not just the number of layers, but there's a lot of other compute impact parameters.
I'm pretty sure that ResNet 100 is about twice as big as 50, so it seems like it'd be something else going on.
Probably. It's
A
good that
question for later.
It's a good question. We had the same question, and good say you found that out. Anything else?
I think you're good. Go ahead.
Okay. All right. This is a comparison of the same model result in a graphical format. You can see that from just accuracy and speed perspective, Inception V2 looks good to us at this point. But I'm expecting TensorFlow to add more and more models, like for our backbone. All right. I'll just show a quick demo. So I'm logging into our office computer here. I'm going to do only the inference. Okay. Let it run. It's all done.
For people in the back, put a thumbs up or down. Is the screen resolution large enough to be readable? I think they want it larger.
Sorry about that.
He's getting it set up.
Okay, can you see this from now? Better? Okay, thank you. So right now I'm using this is just because this is all spaghetti code here a little bit. So I'm using the ResNet 101, okay, which is the most accurate but slowest, okay, that's what I'm using. I'm taking some sample images. All right, it's all good. Okay, this is the image I took. Now it's doing the inference. As expected, it should take around 4 or 5 seconds. Okay, it's done. Here you go. So this is having this fire. It found the fire. It said there's a fire here. This is a smoke, and that's what it's saying. It's a smoke. Okay. This is the prediction. This is the input image. This is the test image with the prediction on top of it. So you want to see this one, I think. this is the one. Okay, this is the ground truth for the smoke. This is a smoke, right? It's the prediction. The ground truth is like this. You can see that this because it's drawn by this tool. You can see that it's not that smooth. Whereas the prediction is pretty smooth. That's what it's showing.
That kind of gets me back to your 85%.
Your microphone?
So this gets me back again to your 85% number. It seems to me you're drawing pretty good boundaries around the smoke.
Yeah.
The algorithm.
Okay.
So on the other hand, it looks like your mask isn't all that great in terms of the test set that you have.
This one, right? This one.
The left is the ground truth looks pretty shitty, and the predicted mask looks correct.
Fair enough.
Okay. Right?
Fair enough.
So we're
Okay.
talking about you were looking at your measures of accuracy. Is it maybe due to the fact that your ground truth just wasn't drawn?
Fair enough.
Well?
No, I see your point. If this had been more accurate, then probably our prediction also would be more accurate. I agree with you. See, from our perspective, our particular use case, we are not worried about the exact area. We are not worried about the contour.
So what are the false positives that have come out? When something's on fire,
It's tough. In image segmentation, it's tough to measure because you are going pixel by pixel, right? You have to see it from your use case perspective. Our use case is not a medical image where you're looking at cancer patient's pixel or that kind of a thing. What we are doing is straight, we are saying, okay, is the smoke bigger than the fire? It's a very simple question to answer, right?
And what's
So,
that, like a ratio,
What's the ratio?
volume,
If
what's
it's-
the amount of pollution?
you need to see an example that was bad. That is something that you just.
this is bad. What you see is bad. This is bad. This is bad, very bad. Because you should see only fire. The chimney is doing its job, only fire should come up. You should not have any smoke at all. If the smoke is over 20-25% of the fire, then there is a problem because things are not burning.
He's not asking about bad in the use case, he's asking about bad in the recognition.
Oh, in the recognition.
Am I understanding?
Okay. So in the recognition is, as long as we are over 80% accurate, we should be okay. Okay, all right. So this is one example. Okay, got it. More question there.
So can we also look into few of the false positive images? For example, what really will happen if there is a sun in the image? Will it recognize as a fire or what would the
We don't have examples like that, but that's one way to verify whether it's going after the sun and other things. I've seen things where it's looking at a lamp and it says, no, it's not. It's not.
So I'm really curious to see what really will be the false positives.
I mean, we have examples that are a picture, but there's a parking lot in the front. And the parking lot could have cars with their headlights on. It could have a parking lot light glaring down on the parking lot, and then the smokestack would be behind it. And so there's things like that we have to deal with as challenges.
So in such situations, how are we handling the false positives, for example, the headlamps?
Like this gentleman was saying, we can have better labeling. That's number one. Another thing to think is we also have a chimney there, the third one, right? We can also force it to look for the chimney
As a third class.
as a third class. So it knows that all these three together. So our original model without mask RCNN, we had done it that way only, so that it knows that it has to look all these three together. So even if it sees a fire somewhere else, it will ignore it.
So does it mean like in these cases, all the false positives categories will be differently? For example, sun, chimney, the lamp, the headlamps. Will that also come as a separate?
No, it won't. Because what we are doing here is it actually looks for some kind of precision number. If the IOE is greater than or equal to 0.5, that's the only one it's going to show. The other ones will fall below and it won't even show at all. So the way I would go about doing that while developing the model, I see that as like a residual analysis. I'll look at the images for the known problems. I'll look at what's going on there, and I'll try to tune those kind of situations. You had a question. Sorry, one more question here. Okay. how small the class can be, the mask can be?
We haven't tested the lower limits on a minimum number of training records because, I mean, we're trying to get enough to be general to go into production.
Yeah.
So we don't want to have a minimal number to barely work. I understand the question. It's a good question. We're not trying to necessarily do a study exploring every parameter limitation.
So why not? Even if you have a higher resolution image, it may not help.
Yeah. You must be surprised. Sorry, go ahead.
I think the question was, what is the size of the fire in the picture? Smallest size of the fire.
Do you want to
Smaller
speak?
size. Smaller size of the fire in terms of pixels, right?
Oh,
In terms of
okay.
pixels.
Oh, I misunderstood that. Okay.
So in terms of pixels you are talking, right? We haven't measured that, but it pretty much gets even the very small numbers, it gets it. I have seen it. In some situations, I have seen that it not getting the fire, the initial fire. I'll show you a video where we were going in steps. The initial fire, it did not get it. Once it became a little bit bigger, it got it. But from our use case perspective, we are fine. Fire is not an issue here, right? The fire, then smoke comes. Then that's where our problem comes into
Yeah.
picture. But still, that can be tuned too.
Question?
Okay.
But it is very windy and the smoke is like very spread out.
Yeah, this is windy. This is windy.
Yeah, it's going at a 45-degree angle. It's
Yeah,
windy
this is windy.
But if it gets,
Spreading the smoke, right, it is kind of, you can detect this as a contrast to the flame very easily.
I mean, it gets down to us labeling images. If we have labeled images with very thin smoke, then it'll train the model to learn very thin smoke. And to the extent we can have a variety of conditions, of different weather conditions, with, say, clouds in the background or hills in the background and things like that. So it gets back to speaking to, part of the data science project is gathering data and how much you want to be robust to, how much you gather data to.
You have to use different models depending on the weather, is that how you work?
No, we
I
can
mean,
use
just for gathering records for training, we'll pick the best model, but not necessarily change models if it rains. But it doesn't rain much in the desert.
Strictly from a presentation point of view, it'd be nice to see some confounds, that is, stuff that you have a hard time.
Got it.
Yeah, most of the confounds, just to repeat the question, it'd be good to see more confounding or difficult challenges. And so a lot of the problems is it's getting in the ballpark area. It's easy to get a 10% overlap. The challenge is getting to like a 90%, 99% overlap. So the models are very good. Transfer learning is very good. But, if you're expecting us to highlight a football, that's not the kind of problem we have.
Yeah.
So, I mean, as far as the type of confounds, it has to do with the area of overlap, intersection over union. A question in the back with the microphone?
Yeah, so first of all, this code that, so TensorFlow, you're using TensorFlow object detection
APIs, yeah.
I'm pretty new to this, but am I to assume that it's providing the code which one can kind of work with a little bit?
So what that TensorFlow APIs?
Code derived from there, what we're looking at?
Yeah. So the TensorFlow APIs provide basically in a typical TensorFlow program, you have to construct your own convolution network, right? And then you have to write your loss functions, whatever it is, and other things. Then you have to train it. All those things you need to do. What they have done is they have done everything for you. They defined the network, ResNet 101, 50 and 101, everything they have done it. And they even trained it on the COCO dataset. They got the model and everything. So all you are doing by API, you are just loading that model. And you are going to train only the last two layers, whatever layers they have allowed you to do. They don't even allow a lot of different messing around with the transfer learning too. You have to supply your data, labeled data, and they have given you a nice configuration file where you can specify different things like I mentioned. How many steps you want, do you want a different loss weightage you want to change, those kind of things you can do. And they also given you a nice IPython notebook which you can use as a reference to start with. But you have to write your code.
He wants to ask a
The
question.
next question,
Sorry.
basically going from what you just talked about a few minutes ago, which is supposing there's a third fixed feature on the image.
Yeah.
And we want to kind of like have a expected distance to that. Okay. So to that extent, can we hook into the penultimate layer and access the value and
Yeah, so the way we did it in a different way. I see what you're saying. So when it's looking at smoke and fire, it not necessarily connects them together. You can have a smoke here and connect. So we did a post-processing after this to combine those two. And it was not, that's what we did. There could be other ways to do that. That's one way we solved the problem. Because we could get 2 smokes and four fires, which, yeah, we didn't model, we didn't change. If we have to do it ourselves, we will make sure all those things, 3 things are together. We can write, kind of associate our loss function along with that and make sure everything is fine. Because we are just going with what they have given. We did some post processing to make sure we can connect the fires and smoke together. Okay. Any other questions? Oh, here, there's one more here on this side.
For the false positives, have you seen any false positives with either smoke or fire, other than activity?
No.
I don't want
Maybe.
We've got one that's trained on some public data and then a private customer project. I don't want to go into a lot of the details as far as a private customer project. So as far as what we have here is more general public for the talk here. And so we haven't tried to be exhaustive on every corner case of different weirdness that may come up.
Okay.
Maybe we can continue on, Ravi, with the demo just to get that done.
I'll just finish off the demo, right? We are running out of time here. So here, if you see here, this is a part of the video. The fire has just started. And if you see here, this is the test image. This is the test image with prediction. Where is the prediction? No, it didn't find it. This is one of the cases it did not find it. All right? So let me move on. I just did not make this as a video. I'm manually going to move things around here, right? So let me do this. This is the next video image. It found it now, right? It found it now. See, for our use case, this is okay because we will be seeing multiple times. If we have to detect the smoke 1 second later, nothing is going to go wrong, right? Right now, people are waiting there looking at the chimneys. That's how people are doing it now. It's a lot better than that, right? So now it found the fire. So let me move it a little bit more. Where is my cursor here? I'll move to 10. Again, still it's fire, okay. We move to 13. So it has got a smoke coming through. You can see the second class. In our situation, this smoke is okay. Right now, it is just starting. Okay, it's okay now. So now let's go further down. It's bigger. Smoking is getting bigger. See, it didn't find the whole dark thing as a smoke. It got the smoke correctly, which is a good thing, right? All right, this is getting worse here. Go ahead.
And that's just the opposite of the question about, well, why not just detect the overly white stuff? You could say, why not detect the overly dark stuff and call that smoke? But there we had some stuff that was very dark, but it wasn't in the region and the shape of the smoke training examples.
See here, if you see here, this is a fire, and the smoke is somewhere like this, right? It thought this is the whole thing. That's what it has found out. This is when our use case kicks in, right? So for us, this particular one, it's good enough. But if you are going to look at a microscope, a tissue of somebody and going to detect a cancer, you may want to go for a different kind of a precision at that point, right? Image segmentation problems. Okay, so I'm almost done. That's all I have.
Just a minute. Gautam, can you check online if there's any questions from the remote audience? Or maybe just ask if there's any questions.
The good thing about what we showed you today is mass RCNN from a concept perspective has evolved a lot in the last few months or just 1 year. And we've got a beautiful API right now, which along with the transfer learning, you can actually generate mask RCNN based model with 200 plus images. With one GPU box, within a day you can do it. So all the tools are available. It's all open source, right? Okay.
Thank you very much.
Thank you.